Recording's rolling. It is Monday, March 10th. Daylight Savings Day. So pick up where we left off about last week. Guys, remember last week we were doing some rotation, some centripetal force, like stuff. By AP's book, we're going to go into gravitation and orbits. Here, I got Kepler's laws keyed up here. This week I do want to fit in some multiple choice questions and also an FRQ. So got some that I'm looking at, but the next couple days. All right, so here, show you guys this one. So if we go back to Johannes Kepler. Now he actually predates Newton. Historically, he was just making observations of planetary motion. Came up with these three ideas. Planets actually move in ellipses, not circles. Although in this class, we usually just assume it's circular orbits because it's not too far off, right? The difference between like an actual circular orbit and the elliptical orbit, say like Mars going around the sun, is not that different mathematically. And so here, now the fact that it actually is an elliptical orbit, guys, right at this point, is the planet going really fast, really slow? Really slow. And right over here, it's going really what? Fast, right? Now, in terms of energies, what type of energy? I should say, is
potential.
Yeah, more potential here, right? More potential, less kinetic, right? And over here, it's more what, less what? More kinetic, less potential, right? But if you add up the total mechanical energy, kinetic plus potential, what do you know about it all the way around? It's the same all the way around. I've seen that AP asked that question multiple times in the past, so there's a good chance you're going to get exactly that question too. Right? Right. Second law, he realized equal areas and equal time. So to say it takes like 30 days to go from here to here and 30 days here to here. Size of that wedge, same size. Okay. And then his third law, he really just came up with this proportion. He said guys, what does this capital T stand for? Time. Yeah, time period. Now for Earth, that might be 365 days, right? How much time does it take to go around once? So the square of that time is proportional to the average distance cubed. Notice I'm saying average distance because, of course, it varies a little bit because it's actually elliptical orbit. Okay. Now, when you bring in Newton, and you can make this an exact equation, right? You got a 2 pi and the whole thing, right? You got universal gravity constant here. Right? Guys, which mass does this represent? This is the mass of what? Here, guys, suppose this is Mars going around the sun. Is this in the mass of Mars or mass of the sun? Mass of the sun. Yeah, it's mass of whatever's being orbited. Okay. So if you're watching a moon go around a planet, I'm gonna have you guys solve that later today. Do you guys think you can solve moon go around a planet? This would represent the mass of the planet in that case, because that's what's being orbited. Okay. Okay. Now, see, inverse square law is about to guys, here's an example of inverse square law between gravitational force and distance. Okay, so proportional to 1 over the distance squared. Okay, so here's a light example of this. Okay, so if you say you got your eyeball like 1 foot away from a candle flame, and then 2 feet away, and then 3 feet away. Okay, you guys see the amount of light that your eye would catch is proportional to 1 over the distance squared. Okay, so gravity works the same way. So does electric field. A lot of things in physics taper off 1 over the distance squared, okay, and it's a consequence of living in 3 spatial dimensions. Okay. So you got gm over r squared. So there's your gravitational force. That's going to show up here, guys, on your AP equation bank. It's organized a little bit weird. It's right here, right underneath Newton's second law of motion. There's your universal gravitation. Okay. And then what we got? We got friction and Hooke's law and centripetal acceleration and kinetic energy and work and so many stuff. Okay. And then all the way down here, now there's gravitational potential energy. They got both forms of that. So you guys know the organization of that. Guys, which force is bigger? The Earth pulling on the moon or the moon pulling on the Earth? The same. Equal. That'd be Newton's third law, wouldn't it? Newton's third law. Ooh, all right. It's challenge time. You guys woken up enough? You guys ready for this? Ready for this? All right. I need you guys to derive from scratch orbital speed. And when I say from scratch, remember, you're allowed to use formulas off this page as a starting point. All right, so you're allowed to know everything here. Say, okay, take this as given. Okay. So derive orbital speed. For example, say it's 1957. We just watched the Soviets send Sputnik around the Earth. Everybody's freaking out. We're doing some mad calculations right now. I broke out our slide rule. We got to figure out how fast we got to send a rocket around the Earth. Otherwise, we're all gonna die. Huh? Yeah. Thank goodness somebody solved this. That's how we won the Cold War.
It's a valid concern. If you die, you're dead.
What do you think about that one?
It's under philosophy. Yeah, it's very inconvenient for you. Yes, too much pressure. So that was that evil corporation.
How fast you have to send a rocket, keep it in orbit around the Earth? Okay. Here. Show you guys some hints, help frame this just a little bit. Okay, so find orbital speed in terms of, here, let's get a diagram going. Here could be the Earth. The Earth has some mass, I'll do capital M, mass of the Earth. Okay, we're sending around a little satellite. Maybe this has mass little m. Okay, let's say it's going just above the atmosphere. And if that's true, then the radius of this orbit is pretty much the radius of the planet. So we'll just say it's the same thing. Okay. Okay. Because like 400 kilometers above the atmosphere, it's okay, it's not that different. Okay. I think there's also a universal gravity constant. So we need universal gravity constant. Okay. We need well, here. Got the mass of the planet, the mass of the satellite, the radius of the planet. Am I forgetting anything? We should be able to do in terms of that. All right, see how you guys are doing. Where's it gotta be?
There's one, it's a space stuff.
And looking for it.
I'm going to remove the bomb.
Okay. Go ahead, say equals. Yeah. All right, here on the right track. Yeah. That'll get today. Where's the prayer? Okay, so that's gravitational force. Yeah, you need that. Let's see, it's orbiting, it's moving in a what kind of path? R squared. Okay, yep, that's a good start. Need that. R squared. And you need that force. I don't get this. You're really close. Happy man.
You said you want to touch me?
Oh, R squared. That A could be that's like Jim over R squared. Okay, you're really close.
That's what the downstairs. The time period revolve around that. It's a 0.01% paralysis. You really do it. You do it. You really just don't gamble now.
Alright, let's take one more trip around the room. See if anybody's getting this. Right. No, yeah, she doesn't show.
Fine, because that's the ratings it takes.
Since I think they maybe got it. Let me check the work.
That's just breaking.
Oh, I think I told you. Yeah, it's not helpful. Right, here, if it's on a curved path, what kind of force does something on a curved path? Alright, yeah, you got it. So that's what I should have told you. Yeah, that's it. Got it.
Yeah, that's what I was thinking. Oh my goodness.
Sort of is. Close. It's close.
We can move this gets on, we're just without church stuff. Oh, she just said it. That's your.
Alright, Hans got it. Hans got it. Alec got it. Hector got it. All right, I got 3 winners. 3 winners. There you go. All right, so actually, this is a tiny picture. I'm gonna blow up this picture quite a bit here. So here's the planet. Here's the satellite. You know, what could be helpful is if I get a 3-body diagram on the satellite. So here, say a satellite's on this dashed line path, which is a curved path. It's got this instantaneous velocity like this. Okay, guys, if you draw a 3-body diagram, here, switch to ink color. 3-body diagram. What is the what's one force on the satellite? Yeah, gravitational force. Gravitational force. Okay. Yeah, you could say mg. That's true. Can I put this in more universal form? F sub g equals. How about g m over r squared, like that? Okay. And guys, what is this capital G capital M over r squared? That could consolidate to what? Yeah, gravitational acceleration, right? Like the gravity field of a planet. And that is little m times little g. You guys see that? That is the same thing as little m, little g. It's just expressed in a more universal form. It's the same thing. Okay, here, let me write that up here in case you don't see it. So when I say gravitational force, that's g m over r squared is mg, because this bit right here, the universal gravity constant, 6.67 times 10 to the negative 11 Bush units, mass of the planet, radius of the planet. Put that all together, that gives you the gravity field of the planet. Okay, here's little m is the mass of the satellite. Okay, same thing. Okay. Now that force. Are there any other forces on the satellite? No, that's it. That's the only force. Okay. So is it in free fall? Yeah, sure is. Sure is. But it's going so fast to the side that it's falling around the curvature of the planet. Okay. We're going to call this orbital speed. Okay. And who knows the formula for a force to hold something on a curved path? How's that go? mv squared over r. Aha. Okay. So it's going to go centripetal force is being provided by the gravitational force. And you guys just told me centripetal force. Well, that's your mv squared over r. And gravitational force, okay, that's all this right here. Gmm over r squared. Okay. Guys, what variable completely cancels? Yeah, and that's the mass of the what? Mass of the satellite. So if you have a heavy satellite next to a light satellite, do they need to be going at the same speed to stay in orbit? Suppose you're an astronaut, you go out on a space block, you got your little tether, right? You drop your wrench, your space wrench goes floating on, right? What's more massive, the spaceship or that little wrench? Spaceship. But are they floating side by side all the way around? Yeah. Yep, that's exactly what that says right there. Right? Okay, I guess one of the R's go away. And then if you're solving for this V, one last step is to take the what of both sides. For v and its orbital speed, and it's for a circular orbit. So that'd probably be written out like circular orbit. Okay. Square root g m on r. Okay. Universal gravity constant. You guys know g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay. Mass of the planet, radius of the planet. It's all right there. Okay. All right, so here we go. So here's the poster version. Centripetal force is provided by gravitational force. There's centripetal force, there's gravitational force. And to point out where these formulas are on your equation bank, here's gravitational force, GMM over r squared. Okay. Now, centripetal force is not exactly on here, but it kind of is. Right? Here's centripetal acceleration. So, I think they would take this. I think you're allowed to start with that anyway, because it's so close to what they have anyway. I don't think they're going to count off if you start with that. Okay. And then, the mass of the satellite cancels, the R partially cancels, and there's your orbital speed for a circular orbit. Okay, circular orbit. Okay, you guys got that? Okay. Critical thinking question. Suppose we backtrack a little bit, because Kepler said, well, realistically, I'm looking at all these planets, I don't see true circular orbits, slight ellipses. Okay. Because why are actual circular orbits not really observed in nature? Why is that? Yeah. Because in reality, the solar system's a little bit sloshy. It's something called the three-body problem, where you can't predict like exactly where something's going to be without like really sophisticated computer model. So like if Jupiter swings by, it's going to knock something a tiny bit out of orbit. Right? If there's something that was a true circular orbit, and for any reason it gets bumped a little bit closer to the sun, it's just going to spiral into the sun. So it's not really stable. But ellipses are stable. Right? But that's okay here, because pretty close to the circle. Right. Ooh. All right, you guys good with that? That's good. That's good. All right, next one. Suppose you got a planet. It's got mass m. It's got radius r. Here, there you. Gravity constant, in case that matters. Can you guys tell me what is the density of the planet, and then later on, what's the gravitational field of the planet? Okay, go ahead. Write it in terms of the variables that are on this page: m, r, and capital G. Yeah, that's all you need. What's the assume the planet was uniform density. Maybe that's not completely realistic, but let's just say it's the same density all the way through, just to simplify it a little bit. Okay. What is the density of the dirt on this planet in terms of its mass, its radius, and well, you have universal gravity constant if that matters. What's the density of that planet? Actually, I got two posters on this one, so this is just the warm up to the next poster, really. Ah, yeah, you guys catch that? You guys hear that? Mass divided by volume. There you go. Yeah, so that's the first step. Oh yeah. So guys, density is a ratio of what to what? Mass over volume, right? Okay, well, mass is m, so you got that. Check. What's the volume? Yeah. Okay, Hans got it. Yeah, Alex got it. Okay. But yeah, getting pretty close. Close. I bet some of you guys are real close here. So you guys said mass over volume, and we're talking about the volume of a sphere, right? Yeah. Okay. I think I did know some of you guys, but if you got that, awesome. Because volume of a sphere, that's a good one to know. Volume of a sphere is 4/3 pi r cubed. Right? I don't think you'd be expected to memorize that. They might tell you the volume of a sphere and then want you to figure that out. Okay. Here's what I think you really should know, though, is that volume is proportional to r cubed. You should definitely know that. Okay. Right. And then, okay, you got more space in your brain than 4/3 pi. Okay. You guys got. Okay. Do they tell you? Yes. Let's see. Do they tell you the volume of it? They might. Oh, okay, they do. Yeah, good call. It's right here. Here's volume of a sphere. It's on the other side. Right. So usually I refer to this side with all the formats, but on the other side, yeah, they got some prefixes, they got some trigonometry, they got some universal constants, and they have some geometry down here. Yeah, here's a little triangle. Here's your trigonometry. Here's your yeah, straight down. Good call. It's right there. Boom. Okay. Oh, next question. What's the gravity field of that planet? Is this one straight off the page? If it isn't, it's really close. Yeah. Okay. What'd you guys write for gravity field? Yeah, GM over R squared. I think you guys should know that one, right? All right, you guys get there?
Yeah.
All right. Like I said, though, really, this one's just a warm up for the next one. So now that you guys got that, all right, here's the real challenge. Suppose there's some planet X out there, and it has 3 times the radius of Earth and 7 times the mass of Earth. So we figure all that out. Okay. What would the relative density and gravity field be? So what's the planet made out of compared to Earth? Is it made out of lead? Is it made out of styrofoam? Okay. And then follow-up question is, suppose we send an astronaut here and he's running around on the surface. Does he feel really light or really heavy? Okay. He's 3 times the mass, or sorry, 3 times the radial size, which has one effect, but sometimes the mass, which has a different effect. So what's the aggregate effect? The more mass of the planet should make it feel heavier. The larger radial size, well, that moves him further from the center. That should make it feel lighter. So what's going to happen? Okay. So what's the density and what's the gravity field? Say compared to Earth. We'll do it in terms of Earth. Notice there's no numbers like I didn't give you an actual radius or an actual mass. I'm just comparing it to Earth, right? So compared to Earth.
It only takes one time to get out. I lost it all. One time. How much did you lose? I lost like everything. Like this guy can lose like 200. That's it. No, that's not. That's not. Oh, density. No, that's it. Okay. You got that back figure next time. No. They got on, man. No.
All right, let's start with going through density. So density. Now, back a few minutes ago, you guys said density was mass compared to volume. Now here I have density of the material that makes planet X compared to that of Earth. Right, so it's a fraction over a fraction. Right, is it? Okay. So it's something to do with mass over volume. That's mass over 4/3 pi r cubed. Right. Now, do you guys see that this 4/3 pi and this 4/3 pi is just going to cancel? Okay. So as long as you know that volume is proportional to radius cubed, you'll still get exactly the correct answer because that whole 4/3 pi ratio cancels, it turns it into a sphere. Okay. So you got 7 times the mass of Earth and 3 times the radius of Earth. But guys, that 3 times the radius is getting to the power of 3. Guys, what is 3 to the power of 3? 27. Right? 3 times 3 is 9, times 3 is 27. Right? And then everything else. Here's mass of Earth. Mass of Earth. What happens to the mass of Earth? Yep. And what about radius of Earth to the power of 3? Radius of Earth to the power of 3? And all you're left with is you got a 7 up here. And you got a 3 to the power of 3 down here. So what's the overall fraction? 7/27. Right. So is that planet made out of lead or is it made out of styrofoam? Styrofoam. Yeah. 7/27. Is that approximately a quarter? Okay. So this planet has approximately a quarter of the density that Earth does. It's a giant puff planet. It's more massive. It's also way more voluminous, and yeah, mass doesn't nearly make up for that. Okay. Guys, how many times more massive would it have to be to match Earth's density? 27. Yeah, you have to have 27 times the mass. If it was made out of the same material that Earth was made out of, and it's scaled up the same, you say, okay, if it's 3 times the radius, well, it's got to have 27 times the mass. It only has 7 times. Woo! We got ourselves a puff planet. Yeah. Okay. All right. Is AP gonna ask that? Wouldn't count on it. This next question, there's a good chance you'll get this next question right here. Is what is the gravity field on this planet compared to Earth? check. Yeah, okay. Alright, give you guys a little time to work that out. Maybe some of you guys figured it out already. Yeah, Alec got it. Who else got this? Yeah, Alex got it. Okay, Hans got it. Our explain. Nathan got it. It's gravity.
Yeah.
Got it. Okay. Who else? Who else? Landon got it. Hector got it. Boom, boom.
That happened.
There, got it. All right. I bet you guys are getting this. So, you know, the general form for gravity field is GM over R squared. Right, so I got 7 times the mass of Earth here and 3 times the radius of Earth. You know that 3 times the radius gets squared, right? And guys, what's 3 squared? 9. So far this is 7 over 9. And we got a bunch of other variables. Universal gravity constant, universal gravity constant. Mass of Earth, radius of Earth squared, radius of Earth squared. And all you're left with is 7 over 3 squared. Isn't that 7 over 9? Okay. So we sent an astronaut to this planet. This astronaut's bouncing around. Does that astronaut feel a little bit heavy or a little bit light? A little bit light, but not crazy different. Because 7 over 9. Right. Yeah, but it's a little bit on the light side, right? Right. So you guys be able to figure that out? Okay. This next one. How should I couch this? Well, here. Let's get a draw this next one from scratch. Okay. So here's the scenario. We're looking out at some planet, and I want to know what is the mass of this planet. It's just somewhere out there. Okay. And I see a little tiny moon going around it. Little tiny moon. Okay. And let me check here. Okay. Let's say this distance from the center of the planet to the moon, I'll call R. And here, I'll even give you guys a number. We'll do both, but we'll do it in terms of variables, and then we'll go back and throw some numbers in. Let's say this is 2.5 times 10 to the 8 meters. Right, so we throw some numbers at it. Okay. Of course, I'll give you guys universal gravity constant right here, 6.67 times 10 to the negative 11 meters squared per kilogram squared. So you either know that or know how to find it, of course, on your AP equation bank. Okay. It's point out to you guys real fast. All right, so in order to refer to this side, if we flip it over, that should be, there it is. It's the first one, right there. Okay. So there's universal gravity constant. Okay. And I have to tell you, let's say it takes some amount of time to go around. I'll call capital T time period, right, time period. And to throw a number at this too, let's say it's like 23 days. Okay. So solve for M, which is the mass of the planet being orbited, so the big planet, in terms of universal gravity constant, say the mass of the moon, the orbital distance of the moon, and the time period it takes to go around. Okay. Yeah, so do variables first, and then we'll come back and throw some numbers in and see what is the mass of that planet. Okay. You guys know that's how we know the mass of Jupiter, right? We just watch the moons go around it. Okay. How we know the mass of the sun. All the planets going around the sun. Here, give you guys a hint. If you look at your notes from earlier today, do you have a scenario where a satellite's orbiting a planet? Did we do that one earlier today? Satellite orbiting the planet? So you could probably use that. You could probably ooh, what is the distance around? Do you think it's okay to say that this orbit is approximately circular? Right? Even if it's not exactly circular, it's probably pretty close. I did give you a hard radial size on that orbit, so okay. Probably say it's pretty close to circular. And what is the distance around a circle? Ah, 2 pi r. I bet you're gonna need that somewhere.
Virginia. Why would I go to Virginia? I'm not going anywhere.
Oh yeah. Might be. Okay. Now, in terms of GMR and T, okay, there's G, there's R, there's T, separate T now, G. What is T? Right, yeah, is that the, what's the last one, right? That be different, but it's not huge, there's a company.
Oh, sure.
Did I got here? Yeah, let me throw some other sense at you guys again. So, you guys have orbital speed from earlier today, right? You guys got orbital speed. Right? That's going to be helpful. That's going to be part of solving this orbital speed. You guys derived that earlier today. Now, orbital speed. Guys, speed. Speed is what over what?
Distance over time.
Distance over time. And what is the distance around a circle?
Radius.
Yeah, circumference, which is 2 pi r. You guys said that? Right? So it goes distance 2 pi r in time period, capital T. Right? Put it all together. Right? All the parts just lying around. Close. Close. Not quite. Close. Yeah. Here, I'll show you guys the top half of this poster anyway. Okay, help you out. Okay. So, whoops, not that one. We're done with that one. Try that. So there's your scenario. Okay. We're watching this moon orbit this big planet. Okay. And there, actually, there's a couple of starting places you could have. Right? You could start with Kepler's third law, but the Newtonianized version of it, so you have an exact equation rather than just a proportion to look like that. You guys remember Kepler said the time period to go around squared is proportional to the average distance cubed, right? And here's the exact equation version. It's 2 pi. If you start from the orbital speed version, which is actually what I recommend, this is what I would do. I'd probably just start from orbital speed. Okay, so you guys have this from earlier today. Right, square root GM on R. This is the mass of what? The planet or the moon? The planet. So the thing being orbited. Okay. Ooh, and guys, that V right there, is that speed?
Yeah.
And that's distance over time? And you guys said that's what over what? 2 pi r over T. Can you guys finish that there? Can you guys solve for M? Okay. Now it's just algebra. got everything down. Can you guys just finish that off with the algebra? Got it. Almost. Oh, wait, yeah. Okay. That's one part, Okay, yeah. All right. Got it.
You actually understand me?
Yeah.
Alright.
Yeah, Hans got it.
I have a phone.
Yeah, Jack got it. Hey, got it. Oh, yeah, you got to get this. Correct.
And get your lights down here.
Oh, I think.
Like this guy from.
Yeah. Who else maybe has this?
It's just. They were good.
Figure plus.
I mean, relative of that.
Guys, if this is your free response question, then
There's no straight.
they probably don't want you to start with orbital speed. You would have to derive this from scratch leading up to this. So you guys remember how you did that earlier today? You said mv squared over r equals gmm over r squared, and then you could solve for v, and then you got this, right? And then we're just picking up from that point. Okay. Right, so if you rearrange this with algebra, you get this expression right here. It says exactly the answer. Okay. So here, get rid of the root. You have to square both sides. That's this 2 pi is all being squared. If you did 4 times pi squared, that's perfectly fine too. Okay. This r gets squared, but then you have to furthermore cross multiply this r, and that brings you r to the power of 3. So this t was in the denominator. Okay, that's got to be squared to undo the square root. So e squared. And then finally divide down this universal gravity constant g. It looks exactly like that. Mass of the planet. Okay. All right, so you guys got that? All right. Now, I threw you guys some numerical example here. Threw you guys some numbers. I forgot to give you the mass of the moon. Is that okay? Do you need the mass of the moon? No, has nothing to do with anything. I could have given you a number, it would be totally irrelevant. And so you guys solve that, I'll solve it. Let's see if we get the same thing for the mass of the planet. I got a number on my screen. How about you guys? Anybody got it? Got the answer? What'd you get? I got some other different. Okay, I'll double check my work.
Are we using 23 days? You're doing it to convert that into like seconds or something.
Aha! Yeah! Aha! Luke caught that. You guys catch that? Guys, can you just throw 23 in the calculator for time? Right, you have to convert it into seconds first, right? Okay. Guys, this is 23 Earth days. So convert that into seconds.
Gravitational constant.
Here's your gravitational constant, 6.67 times 10 to the negative 11. That's in terms of base SI units. Yeah, okay. How about now? Who think they got it? Nathan got it.
What's the gravity?
So capital G is use 6.67 times 10 to the negative 11. That's in base SI units. It's not looking. But anybody over here? Alright, yeah, I'll do it with you guys. Okay. So I'm following this model right here. Okay, so do open parenthesis. You got a 2 pi close parentheses squared. Okay? Or you could do 4 times pi squared. That's the same thing. Okay. Right. Then times. And I need distance to the power of 3. That's what this r is, right? Radial distance. So I'm going to open up a parenthesis and type in this r. Now, because this only works if I open a parenthesis first, because I need to cube all this that's multiplied together. 2.5 times 10 to the power of 8. Then close parenthesis to the power of 3. Okay. All right, you guys good so far? All right, so I'm up to here. Okay. Then divide by. Now there's a bunch of stuff in the denominator that's multiplied. So to make sure, I'm going to do this. I'm going to open up an excess of parentheses. Now this particular model calculator, you can open up like 100 if you want. It'll naturally close them. Okay. Right. But see, like here, if I only open up one parenthesis after I hit divide by, as soon as I close it, it stops dividing, and then that'll lead you to the wrong answer. So I have a crazy number of parentheses to make sure that everything else is definitely grouped together. Just a little trick, calculator trick. G, 6.67 times 10 to the power negative 11. Close open. Now the close open in this model automatically multiplies. Different calculators are different, so know how to use your calculator, of course. You got a class set of these there. Okay. But it's multiplied, it's still in the denominator. And then I need time period squared. Now here's the trick that I know Luke caught, and I think some of you guys caught too. The 23 days, yeah, that's time, but that's not a base SI unit. And this is implied Earth days. So guys, how do you turn days into seconds? What do I need to multiply by?
23 times 24 times 60 times 60.
There you go. So times 24 hours a day. So there's how many hours. 23 times 24, that's how many hours. Times 60 is how many minutes. Times 60 again is how many seconds, which is the unit you need. Now close that parenthesis and square that. Okay. Hey, guys got that? Okay. All right. And then enter, yep, that's the same thing I was looking at before. Look at the mass of that planet is 2.34 times 10 to the 24. And what's the unit? Kilogram. Yeah. Okay. By the way, the mass of Earth is like 5.98 times 10 to the 24 kilograms. So, guys, is this planet a little bit heavier or a little bit lighter than Earth? A little bit lighter. But it's comparable, right? It's about what, half the size of Earth, about. All right. Well, that'll be our PowerPoint today.